Well, dear students, so far we have discussed uh, the Raoult's law, in which both the components are volatile, and have already done some of the problems based on that Raoult's law and calculation of moles, mole fraction in vapor phase as well as liquid phase, total vapor pressure, how to calculate total vapor pressure, and how to apply Raoult's law. And this is the case second. We are still dealing with the case second when both the components are volatile, right? And still two lectures more will required here, so that we can discuss all these things. Some theoretical portion is also there in this topic. So in this lecture I will I'm going to discuss this, apply this Raoult's law, and how to use this Raoult's law for the distillation of volatile components from the mixture. Suppose that two liquids were given, and it is asked, okay, do the fractional distillation. So what is the concept behind the fractional distillation and so-called distillation? So in this lecture I will try to discuss that. So everybody is knowing what is the meaning of distillation. Distillation means a method of separation of components from the two liquids, right? And this fractional distillation or distillation is based on the difference in the boiling point, right? Difference in the boiling point of two liquids. So from Raoult's law, it is clear that if both the components are volatile, then definitely that solution will boil at low temperature compared to the actual boiling point. We have already discussed this. So in the distillation, I am taking one example of benzene and toluene mixture. And this mixture forms nearly ideal. Toluene mixture is nearly ideal. I am not saying that this is perfect solution, but nearly ideal solution. Nearly ideal solution, right? Means obey the Raoult's law, as we have discussed in the previous lecture, right? See, benzene is more volatile, means the P naught of benzene is more than the P naught of toluene, right? And all of you are knowing that the vapor is, and also we have calculated the composition of vapor phase in the previous lecture. Now see, vapor is always richer with respect to the more volatile component. This is a common observation, but this statement is valid till your system is ideal. Once your system is not ideal, then you cannot say like this. So in an ideal system, this vapor is always richer with respect to the volatile component, more volatile component. You can write this statement as well here. Vapor is always richer with more volatile component for ideal mixture. But this statement we cannot say that for all types of system. So I have taken this graph. This is mole fraction of benzene. Here this is 1. So this coordinate, this axis will show the vapor pressure of benzene. This is vapor pressure of toluene, and this is the mole fraction of mixture. But here I have shown here mole fraction of benzene, right? And you know, this is the total vapor pressure line as I have shown in the Raoult's law, right? And this is an imaginary line I have drawn here, just imaginary line, and I will explain something here. So see, if you take any point at this line, any point anywhere from here to here, what you have observed that the total pressure, see this line represents the total pressure, right? This is total pressure. P is equal to P naught, I mean P benzene plus P toluene. You can write very simply that the total pressure at any point, and all of you are knowing that the total pressure is the function of the composition of the mixture. So we are not here generalizing that total pressure is always equal from here to here. No, at every composition you have a different pressure. So whenever we are talking about the total vapor pressure of a solution, means we are talking about that pressure corresponding to some of the composition in the liquid phase. Or because Raoult's law is basically for liquid phase, or you can say the total pressure is according to the composition of vapor phase as per Dalton's law, right? Because for vapors you can use Dalton's law, right? But here, since in this chapter we are mainly focusing on the Raoult's law, and we are focusing the composition of liquid, so every time we have to speak like this only. So do not much speak about Dalton's law here. So this total vapor pressure represented by this line, as you know, in the Raoult's law I have shown, and this graph is isothermal graph, or you can say isotherm. This is isotherm, right? Because you know, temperature is constant here, okay? At any fixed temperature, this has been observed. Although distillation, always we prefer basically what we are doing in the laboratory, that is isobaric condition, right? That will also I will explain after this graph, but first I am taking this isotherm, and through both the graphs I will explain you distillation process. But actually this distillation is carried out under isobaric condition, means at constant pressure condition, right? See, suppose that at this imaginary line what I have drawn here, right? At this any point if you take like this, suppose that this point you have taken. Now tell me, at this point the pressure, at this point the pressure means total pressure is less than vapor pressure or more than vapor pressure. See, this is the pressure coordinate. So if you match this either here or here, don't worry. So if you are matching here like this, and corresponding to this point at the total vapor pressure, here you will get, and you will match like this. So at this point the total pressure is less than the vapor pressure. So if the total pressure at the surface of any liquid mixture is less than vapor pressure, then what will happen? Then your system exists in liquid phase or vapor phase. Remember I have told you in the beginning. So if total pressure is less than the equilibrium pressure, our system exists in the vapor phase. So this region, this whole region represents the vapor phase, because you know in this whole region the total pressure is less than this equilibrium pressure. Clear? Good. And oh, that's why I have drawn this figure. Okay. And suppose that any point, if you take here, so this pressure is higher than the equilibrium pressure. So what will happen? Equilibrium shifts towards the liquid side. So this represents the liquid phase, right? So this region represents the liquid phase, and this region represents the vapor phase. And what about this? What I am enclosed here. So you can say this is liquid plus vapor, L plus V. Clear? L plus V. Okay. Now see how to explain this distillation. So I am taking here some numerical values so that you can very easily understand. See, first I am taking, so this line is contact to the liquid line, you can say, and this line in contact with the vapor line, or you can say you can also draw one hypothetical line like this. Also this type of graph also you may find somewhere in some books, no problem. So this whole region is liquid plus vapor region, right? Liquid plus vapor region, but I will explain with the help of this only, uh, because this is little bit more clear. So this point 2, see this point 2, suppose that we are taking okay, so I am taking this point, right? See carefully, all of you should focus here, this point, and this point is A. Let this point is A. So at this point, at this pressure, whatsoever the pressure, total pressure, equilibrium pressure, the composition of liquid phase X benzene is zero point 0.2. So this point A I am writing here, at point A, at A point, because when I will take this numerical value, you will get very easily, you understood this. Mole fraction of benzene is equal to 0.2. So the mole fraction of toluene is 0.8. Because sum is always equal to 1. Now what you can say here, this is the vapor phase and line, and this is the liquid phase line. This line I am assuming liquid phase line, although this is some margin you can take like this, but not required. Okay, you will understand this. So this composition at this point, the total, whatsoever the total vapor pressure you have, in this situation, the mole fraction of benzene 0.2 and mole fraction of toluene what 0.8, right? So if we find the corresponding point in the vapor phase, this is liquid phase, so A point represents liquid phase, liquid phase. So if we find the corresponding value with respect to this, so something here we will find, right? And see this value, like this, and here like this. So corresponding to point 4, and this point I am taking 0.5 basically, so that calculation will be easy. This 0.5, this is 0.4, and this is 0.6, right? Okay, you can scale it. So at point A, so this is now this is point B. So B point represents the vapor phase. B point represents the vapor phase, and now the mole fraction of benzene are 0.5 and mole fraction of toluene are also 0.5. See, dear students, this line represents the any point here below this equilibrium pressure. The total pressure is less than vapor pressure is less than the total pressure, so the maximum component will present in the vapor phase. So I am assuming this is a liquid phase, so corresponding to this liquid phase, the point B is here in the vapor phase. So in vapor phase you have mole fraction of benzene 0.5 and mole fraction of toluene 0.5, and this is vapor phase. Vapor phase. Now tell me, vapor is richer with respect to what? With respect to which component? See, in the liquid phase 0.2 mole fraction, and here 0.5, and now here in liquid 0.8, so here 0.2, so 0.5. So we can say that the vapor is richer with respect to benzene. The vapor is richer with respect to benzene, and obviously this should be because this is what, more volatile component, right? Clear? Good. So although both are equal, but hardly matters is you have to compare with benzene what mole fraction of benzene are in liquid phase and vapor phase, and don't take +2 and +5 is equal to 1, because this is not true. You cannot take mole fraction of benzene in liquid phase plus mole fraction of benzene in vapor phase is equal to 1. So this relation you cannot write at any moment of time. XB plus YB is equal to 1. This relation you cannot write, right? At any moment of time. Whenever you are taking, then you have to, you can write this is equal to 1 and this is equal to 1, right? This relation will not exist anytime. Okay, now it is clear. First you have to understood these 2 points. This is liquid phase point, this is vapor phase point, corresponding vapor phase point. Clear? Okay. Now I am extending this line like this. So what I am doing, I am moving like this, B to C. So what is the meaning of B to C? B to C represents the condensation. Condensation. How we are condensating this? How? The answer is by increasing pressure. You know, when you move from here to here, pressure will increase. So B to C said the condensation. Now after condensation, what will happen? When B to C, you are condensing the vapor. So what should be the mole fraction, new mole fraction of condensate? Mole fraction of condensate. So the mole fraction of condensate are Xb is equal to 0.5 and Xt is equal to 0.5. Because whatever amount of vapor you are condensing, condensate and vapor both have same mole fraction. Clear? Okay. Now, after this is first condensation. This is first condensation. Now find the corresponding point in the vapor phase with respect to this. So when you take, you will find so let it be what 0.7. So now this is C D point, right? Okay, so point D point, at D point, what is the mole fraction of benzene? 0.7. Mole fraction of benzene, Y benzene is equal to 0.7. So Y toluene is 0.3. Now this is the vapor phase. Now see, compare point B and point D. Point B and point D both represents the points corresponding to the vapor phase, but at point D the vapor is richer with respect to benzene compared to the point B. Means after first condensation vapor becomes richer, means in vapor you are getting this. Now if you repeat this process again and you can take DE point. So now this D to E point, what is this? D to E point, very interesting, very informative, but if your focus is not here, you will not understood, right? So D to E movement again represents the condensation, right? Condensation, and whatsoever we get from here in the beaker, this is called second condensate. This is called second condensate. And here first condensate, whatever we are getting here, this is called first condensate. So in the first condensate, you have mole fraction of benzene and toluene 0.5, and now here in the second condensate, you have mole fraction of benzene 0.7 and 0.3. Right? Now see. Right? Now if you repeat again, evaporate this. Again evaporate, so find the corresponding point with respect to this. And right? So let it be 0.9 for simplicity, 0.9 EF. Now this D2E, this condense, and point E is the liquid phase. E point, at E point, the X benzene is equal to 0.7 and X toluene is equal to 0.3, right? Now corresponding to E vapor phase, what is vapor phase in the F? So at F point, this is liquid phase, liquid phase. Now this F point, at F point, uh, this is vapor phase, in Y benzene is equal to 0.9, so Y toluene is equal to 0.1. So now see, your vapor becomes richer and richer. Now if you take the third condensate, so in the third condensate your benzene is 0.9 and so on. If you do fourth condensate, fifth condensate, so you will get pure benzene. So this is the concept of fractional distillation, right, dear students? So how we are doing this? First, we are taking, evaporating some, taking in a container some liquid mixture, what we are supposed to separate them, taken, taken at equilibrium. Now vapors will taken out, they were condensate. Then that will evaporate. Again vapor were collected and condensate. And like this, if we are repeating, continuously repeating this process, finally we will get one pure component. But this is possible only when your mixture is ideal or nearly to ideal. Okay. So this is one graph which is known as vapor pressure versus composition. Composition at constant T. T is constant, right? So this is vapor pressure versus composition curve for ideal system at constant temperature. But what I have told you, that usually in practice we are not preferring this type of distillation at constant temperature. We generally prefer, I am not saying that we cannot do, but we prefer, because you know, constant temperature, constant pressure system maintenance is much easier than constant temperature system maintenance. So we always prefer for distillation constant pressure system, right? So the next graph we will see pressure versus temperature versus composition curve. Temperature basically versus composition. Right? Temperature versus composition at constant pressure means isobaric, right? Isobaric. So this is the preferred method of distillation. Okay. See, dear friends, to save the time, I have taken this picture correctly. See, this is temperature versus composition curve of the same mixture what we have taken above. I have taken the same and same benzene from here to here. This increases from this to this. It is increases, and this is what boiling point of what. We can say, see here what I have taken, toluene. You know, vapor pressure and boiling point are inversely related. So boiling point and vapor pressure, they are inversely related. Vapor pressure, right? So see here, this is what vapor pressure of toluene. So vapor pressure is less, so boiling point is more. And here vapor pressure of benzene is more compared to the toluene. So see this. And sometime you may put a mirror here, and we can say that the boiling point versus composition, or temperature versus composition curve is the mirror image of this. I mean, invert this point, means whatever the value is minimum, so put it maximum, minimum. So this, and reverse this, vapor phase above, liquid phase below, right? See how here, what seen here in this graph, vapor phase is this is vapor phase, and this is liquid phase. You can see the, I mean, same explanation here. Same explanation. You know, if you take any point at this line anywhere, so this is the less than the boiling point. Less than boiling point, because you know this is the boiling point of benzene, this is the boiling point of toluene. And if you know, if you join this, so you will find the equilibrium temperature at corresponding to the equilibrium vapor pressure, because you know, whenever you are taking any pressure in the above graph, that is only at given temperature and given composition, right? So this is the boiling point of toluene. This is the boiling point of this point is the boiling point. So we can say this is the boiling point. Boiling point. Boiling point of benzene. Benzene. And this is the boiling point. Whatever the value we will get, boiling point toluene, right? This is the boiling point of toluene. This is vapor phase, this is liquid plus vapor. Again we will start in the same manner. See this point A. So this is a liquid phase. So point A, at A point, the mole fraction of benzene, X benzene is equal to 0.2. So X toluene is equal to 0.8. Same story. And this is liquid phase. This time we will do quickly. Liquid phase, right? Now see, from A to B, see, from A to B, so corresponding to vapor phase, B line, B point B, see, at this we can take 0.6. So X benzene, sorry, Y benzene is equal to 0.6. So Y toluene is equal to 0.4. See, this is vapor phase composition. So these two are the corresponding point. Means when liquid is richer with respect to what, see, liquid phase benzene toluene is more, but in the vapor phase your benzene is more. So what I have told you in the beginning of this lecture, that vapor is always richer with respect to the more volatile. Here benzene is more volatile, so it is always richer, vapor is always richer with respect to the more volatile component. So at B point is this. Now B to C, this B to C represents the condensation. B to C, see, sometime this adjustment is also important because you people cannot see. So B to C, this is condensation. This is first condensation. Condensation means you are condensing the liquid. Now, in this liquid phase, condensation B to C, in this liquid phase, what is the mole fraction of benzene? Mole fraction of benzene 0.6 and mole fraction of toluene is equal to 0.4. So, whatever first condensate we are taking here, that is 0.6 and 0.4. Right? Similarly, now the corresponding point in the vapor phase, so liquid phase, now you have the same composition in the vapor phase, and both are same points actually. So and also you are knowing that the vapor phase composition and after condensation liquid phase composition is always same, right? So corresponding to this C point, which is in liquid, this is C in liquid and B in vapor phase. So this corresponding to this C D point, which is vapor phase, D point. So D point, what are the mole fraction? It is we can take this as a what? We can take this is 0.9 close, right? So at D point you have mole fraction in vapor phase, Y benzene is equal to 0.9 and Y toluene is equal to 0.1. So when you condense this, see this condensation is shown here. So when you condense this, after condensation you will get in the liquid phase condensation, you will get mole fraction of benzene in liquid phase 0.9 and mole fraction of toluene in liquid phase 0.1. So in this way, if you repeat again and again and again, your one component becomes pure, right? So this is the concept of what? Fractional distillation. Hopefully all of you are clear in this concept, how distillation is carried out for ideal mixtures, right? See, thermodynamics of this ideal mixture. So we can use the formula which you might have derived this formula in thermodynamics. So suppose that we have two components A and B. and they are mixed. A and B both are mixed, and B are represented by red. So B and A, right? So what should be the delta G mixing for this? Delta G mixing for this at given temperature and pressure, this should be equal to nRT XA ln A plus XB ln ln XA and XB ln XB, right? So this should be the delta G mixing. By using this equation, you can calculate the delta G mixture, this mixture. And here all the terms which are used here, they have the usual meaning. See, N here, N are the total moles of mixture, total moles of mixture. XA or the mole fraction of component A, and XB or the mole fraction of B, right? So N are the total number of moles. So by using this equation, you can calculate delta G mixing. More and more delta G mixing. Suppose that T is constant, so R is constant. So what is the variable here? Here the variable is the number of moles, or you can say mole fraction. So with change in the mole fraction, this delta G will decrease. So we can say that a stable system will form with the minimum value of delta G. So when we get this minimum value of delta G, what should be the mole fraction of this A and B? So if you see mathematically, so when this XA and XB are equal and equal to half, right? So XA and XB are equal and equal to half. So when you will get this XA value half, when you mix equal moles of A and B, then the mole fraction is half. So if you take half mole fraction of A and half mole fraction of B, means equal moles of A and B, then as per this equation, this Gibbs energy equation, you will get the minimum value of delta G. And if you want, you can calculate the minima for this, right? So if you draw a plot between delta G, energy, you can say delta G means energy change, and composition. So with composition, you can find out. So what is the value of XA and XB? So at given temperature, right? So I am considering composition as a variable. So when XA is equal to XB is equal to 1 by 2, when then delta G mixing at given temperature and pressure has the minimum value, minimum right? So and you can see mathematically from here also. So you can say this is minimum means less than 0. It is less than 0. That is, this is the least value, minimum value. Right? So when XA is equal to XB is equal to half, then delta G mixing, this is, you know, X is always what, less than 1. So log ln is here. So this value is what, negative and negative. So overall this value will negative. That's why it is less than 0. So you can say that if you mix two components to form a ideal mixture, so it is not, I mean, it will not form ideal mixture when you mix in a variable composition, like one component is 90% and another is 10%, or one is 95 and another is 1. So you won't get, I mean, ideal mixture. Clear to everybody? Yes. In terms of delta G. Now all of you are knowing that delta G is equal to minus T delta S. This relation all of you are knowing. This is equation 2. So you can write delta G mixing is equal to minus T delta S mixing, right? So this relation, all of you are knowing T ds B dP, and you know constant temperature and pressure. We are already say this T and P are constant, right? So when T and P are constant, so you can write this. So you can write delta S mixing is equal to what? Minus NR, put this value, T and T are cancelled, so minus NR XA ln XA plus XB ln XB. Suppose that three components are mixed, so you can take what, plus that also, right? So this is equation 3. By using this equation, you can calculate the delta S mixing of two components. Same story here. When XA is equal to XB is equal to 1 by 2, that is, you can say NA is equal to NB, the delta S mixing delta S mixing is greater than 0 means maximum. Maximum, right? Maximum value. So see, delta G and delta S both were complementing to each other, that when this is minimum value, when this will achieve the minima, then this will achieve the maximum. Same condition. So now what should be the, delta H? So all of you are knowing that delta G is equal to delta H minus T delta S. So from this equation you can write delta H mixing is equal to delta G mixing plus T delta S mixing. See, I used to write this process with delta, and after the symbol, don't think that I am doing wrong something, because in many books you will find delta S and mixing at the end, and delta G and after mixing. But let you know that there is no harm to represent like this. Either way you can represent, but you know, I am following this IUPAC nomenclature. IUPAC suggests that you have to write the process with delta and then symbol, right? So now you can put here delta G is equal to minus T delta S mixing plus T delta S mixing, and this is equal to 0. So how this could be explained, that there is no change in energy. There is no change in energy. This is possible only when the either there is no interaction between A and B, or you can say unlike interaction. Unlike, this is possible only when unlike interaction means interaction between A and B should be equal to interaction between A and B and B. And this will achieve only when the molecular size of the A and B are same, and molecular size is close of A and B, and the forces between A and B, right? Basically, though two factors determine. One is this size, means both the components if have almost same size, and other chemical environment like polarity and electronegativity difference. If all these components are same, so this is the chemical aspect of the solution. So if they are same, then this could be possible, and if this is possible, then this delta H mixing is equal to 0. So there are two factors here for this condition to satisfy, that unlike interaction is equal to the like interaction. This is two possibility. First, molecular shape and size. Molecular shape and size if almost same. And second factor is polarity and chemical environment. environment. So if polarity and chemical environments are same and molecular shape and size are same, then this is possible, right? And see, I have shown here almost equal to. We cannot say this is equal. So this delta H is equal to 0, delta H is equal to 0, then these two conditions are also satisfied. So this is delta G mixing, delta S mixing, and delta H mixing for any ideal mixture, and this is the explanation of this. So for any ideal mixture, what should be the criteria? The criteria is that molecular shape and size of both the components is almost same. Their polarity and electronic environment in the molecule, they are almost similar. This could lead the delta H mixing is equal to 0, then delta S mixing is more than 0, and delta G mixing is less than 0. So this we can explain the in terms of this the thermodynamics of the ideal mixture. Now on a single plot you can explain all these things together. All three thermodynamic factors you can represent very simply, right? See, suppose that this is mole fraction. Suppose that this is mole fraction of A. Here it is 0, here it is 1. So B will also vary in the same manner, 0.2, 0.4, 0.6, 0.8, right? Right, this is what 0.5, and at this point this is the minima and this is the maxima. So this you can say this is energy in a simple terminology. You can say this is energy, right? So see, this is what 0, this is negative, and this is positive. So what is this? This is T delta S. You cannot say delta S only. This is T delta S, and this is delta G mixture, and this is delta H, right? So see, this is energy, this is also energy, and this is also energy. You know what is this T delta S? T delta S is called random energy. Random energy. And you know what is this delta H is called total energy. Total means random plus thermal. Total energy means random plus thermal, right? And you know this random energy cannot be converted into work. That's why if you subtract this energy, this T delta S from this delta H, then you get delta G, and delta G is called energy, Gibbs energy, available in the system for useful work, right? So delta G is basically Gibbs energy which is available in the system for useful work. So magnitude through which this delta G is negative, that is available to the system for useful work. So what is useful work here? Here the useful work to form a homogeneous mixture, right? So this is the thermodynamics of this ideal mixture, right? And one more thing if all these things are valid, then one more thing is there, fourth, because all are complementary. See, one more thing, that delta V mixing is equal to zero, right? Means you can say that V final, you can say that V total is equal to VA plus VB, but all of you are knowing that this is very difficult for any system until or unless both are not have the same chemical environment. If one have some polar bonds or some hydrogen bonding ability or hydrogen bonding dissociation ability, then this will not equal to this. V total is not equal to VA plus VB. But since this condition we are assuming that delta V mixing is equal to 0, so this is always true, right? So for ideal mixture it is okay, but in real situation this is not obtained, right? So this is the total thermodynamics of the ideal mixture, right? So